Swayam Prabha. Digital India. Educated India.
Someone told me that my email was not, my email address was not distributed. So I add with this slide, finally with my contacts. So you have my phone number, my mobile number, and the email address. Okay, so that you can find here. So this will be in the presentation today, so in the PDF at the end. I put also a very short CV of what I've done in the past and so on. Okay, so let's speak about interfacial phenomena. Okay, so first of all, let's take an interface between liquid and vapor. When we are thinking to a droplet, the interface is something that has let's say, meaning at the molecular level. Okay, it's very clear that the liquid has a density of 1,996 kilogram cubic meter for the water at 20 degrees, and then you have the gas. Okay, vapor and that was going out of the droplet plus the air, so something like 1.1 kilogram over cubic meter. So the difference is 1,000. So this big difference in terms of density is happening in few nanometers. Few nanometers to pass from 1,000 to 1, let's say. Okay, so one can think this is, in fact, it's really important to imagine what is happening at the molecular level, because really it's very steep. So it's, the change is really, the gradient, let's say, of density is very, very, very high. 1,000 in 10 power to minus 9 meter, or so. Only when we are going toward the critical point, this interface is going to be broader and broader, okay? But otherwise, it's very, very sharp. It's very sharp. In fact, we can deal the surface tension in a way that we are not considering the interface itself. It's a kind of boundary condition. So we are thinking that the interface has zero thickness, okay? Which is, in fact, is not. But it's important, say, as a simplification. And in many cases, it works. We are going to see today VOF, the interface tracking methods, so VOF, level set, and so on, and they are able to do very nice simulations of what is happening, considering the interface as a very sharp interface. Okay, so the origin of the surface tension of the interface is, of course, linked to the fact that we have a different energy configuration inside the bulk and when we arrive at the interface. In a very naive way, but it's already enough to understand, if you are considering one molecule in the center of the system, there is an interaction in a different direction. Okay, so in 6 different directions, if you consider a cube around the molecule. So we have 6 faces, so we have 6 possible directions. But of course, when we arrive up to the interface, this is becoming only 5, because we are missing one face of this. So the fact that we have less faces in this sense is decreasing the fact that the binding force, the bound that we have between the molecules. Okay, this means that there is an enthalpy change, because the enthalpy is linked to the binding energy of the molecules. So this means that we have, in fact, more attraction toward the center with respect to what we have outside. And this kind of missing binding energy that exists at the interface is creating a force. It's creating a force. And this force, at a macroscopic level, is called surface tension. Okay? Is a way to think about that, but I think that is enough clear. Okay? And this means that since it's a force, may be considered also a pressure, because we have a given area, and so if in a given area we are missing the binding energy, this means that we have more attraction, let's say, toward the internal side, so toward the bulk, and so we are creating a pressure in the system. Okay, so this is the first point. Of course, the Gen is a Nobel Award person in France. I had the pleasure to meet him and to assist to one of his lectures. It was very, very interesting. And he said something at the time that, let's say, I put here, that the molecules in the bulk, I can try to do the French accent, but he said, oh, the molecules in the bulk are very happy. They don't want to escape. And so they would like to re-enter in the bulk when they're at the limit. So they are like an edge, no? Where you're running and then there is an edge. Oh, I don't want that. So coming back. So it was very funny. And then this means that we have, let's say, a kind of repulsion from the edge. Okay. Pay attention to another point. The molecules at the edge, of course, they don't want to continue and to fall down, let's say, in the vapor. But also they can, in order not to go there, they can also go to the right and to the left. They can walk on the wedge. Exactly. So, in fact, the surface tension is something that is going in both directions, in one direction and the other, if you think the structure. So, because the force is distributed, okay, because the force is resisting a stretch of the interface, okay. Someone is always thinking to the, let's say, to the metaphor of having the surface tension. Oh, yes, it's like a membrane, but it's of course wrong, okay? Because the force in a membrane increase with something like a spring, no? Is increased with the area, or let's say the length. In this case, not. Surface tension is a number, okay? Surface tension is a number. Of course, at the nanoscale, we may have the so-called Tolman length. So the surface tension depends then on the scale. But this is something I'm not going to treat this. You can read one of my last paper. By the way, I put all the literatures in 4.3. So today, in the last lesson, you're going to have 4 pages of literature. I put all the literature that I cited in these days is at the end of the 4.3 with the books and also with my papers. Okay, so you're going to find the paper that I published recently in Nature Communication is about simulation at the nanoscales, and there I'm speaking about the change of the surface tension with the scale. Okay, Tolman length, but it's okay. It's another things. Okay. Okay, so surface tension is not depending on the curvature. It's not at the first order. It's not depending on this. A macro scale or micro scale is not depending. Okay, so this is a point. We can even evaluate the surface tension in the sense that, for example, in the first, we can say that as the first approximation. Okay, we can have that epsilon. That is this kind of binding energy is in fact proportional to the mass of the molecules multiplied by the enthalpy. I said that the enthalpy is related to the binding energy. Okay, so since the missing energy is 1/6, because we had inside 6 phases and above only 5, so we're missing 1/6 of the binding energy, is something to say, oh, we are missing 1/6 of MH. Is it right? Okay. So then we can write that is 1/6 of the mass, means at the macro scale the density multiplied by an equivalent length of the molecules. So let's say this kind of size of the molecules. And what is gamma? What is the surface tension? Is this difference of energy divided by the area. So in this case, the area, if we have equivalent lengths, is nothing else than L square. Okay? So at the end, we're landing with gamma, which is in fact 1/6 of what? Rho L, a dimension multiplied by H, the enthalpy. Now, we know the enthalpy of water, for example. Enthalpy of water is 2.6 megajoule per kilogram Kelvin. So, okay. Again, there is a problem of passing from my presentation to here. Accept this. We know the density, no? And we have the size of the molecule of the water is somehow known. Is about, let's say, 3.3 Armstrong. So it's at 0.3 nanometers. If you put everything inside, you obtain a value that is in fact a double of what is really, because there are other effects that are not taken into account, but only to say that it's not 10 times or let's say 1/10. So, okay, it's an estimation. But in this way, it's very clear now, I'm presenting in this way because it's very clear now that gamma, surface tension, is coming really from the energy that is missing at the interface divided by an area. Okay? What is happening in reality is something like that. So if you're considering, for example, the generalized van der Waals theory, it is possible to define the thickness of the density. Okay, so the thickness of the density has this kind of equation. Usually we are using the hyperbolic tangent. Okay, and the dimension here is really, we are really thinking to nanometers. Nanometers. Not only the thickness is also a function of the temperature. Okay, and one can also write how is the form of the function between delta, the thickness of the interface, and the temperature. And you can see, as I said before, that the critical temperature is really the big factor. So if you're going in direction of the critical temperature, this one is -1, but it's logarithmus, there is a logarithmus there, and there's -1. So it's becoming very broad. Practically, at the critical point, this interface is becoming infinite. So in fact, there is no difference anymore between the liquid and the vapor. Okay? So, we are, one can say, well, since you have a hyperbolic tangent, where is the end? Or because it's an asymptotic function, where is the end of the thickness, let's say? One can think about 10 and 90%, this is very clear. And so at the end, the so-called Gibbs interface, that is in fact where we have 0.5 rho L plus rho V, this can be taken as a mathematical position of the interface. Okay, this is a simulation of the interface somehow, but of course it's a molecular level, and we can even recognize by eyes that this must be something more, let's say, dense. So this is the liquid and this is the gas. I did many molecular dynamic simulations, so it's possible to see this effect when you have droplets and so on. Okay, surface tension. Well, we already know that surface tension is linked to the force, but then when we translated this concept to the thermodynamics, for us we can work with the work. We can work with the work, sorry for that. We can use the work, okay? So, in fact, as you remember, I announced already that the work in the thermodynamics equation can be written is in terms of generalized work. It's not only minus PdV, okay? But it can be sigma dA. So it's related to the surface tension. So in fact, let's say what is happening is that the external forces must perform positive work against the interface surface to increase the total area of the surface. You need to blow to produce a soap bubble. So you need to do to act in order to stretch the surface. In this way, let's say the molecules are very happy, but you need to work against their will. You need to push them toward the interface. They don't like. Okay. Okay. So this is the situation. Okay. So in terms of equation, we can write that the force the total force linked to the surface tension can be written like sigma dl cross n. N is the vector normal to the interface, and dl is one of direction, can be also the normal direction. So we have different directions. In fact, it's possible to describe the entire surface. Okay? So the point is that when we are thinking about water, for example, we have an homogeneous situation. But if we are putting, for example, a surfactant inside, then the situation is changing. So we may build structures where the surface tension is more in one direction with respect to the other. So in fact, the system is becoming non-isotropic. And so this means that the force, we have a force in one direction and the force in another direction. Okay? We are going to deal only with homogeneous system today, okay? But only to know that when we are doing something like when, for example, we are acting surfactants and so on, the surface tension is changing also because, for example, the surfactants are going to build a structure on the skin of the bulk, and this is changing also let's say, really the forces, okay? With soap, for example, detergents, and so on. And there is a very nice chemistry of the interface with such components, which is very interesting, and of course is very important also for, let's say, biology and biology. For example, the breath is linked to the presence of lipids that are changing the surface tension, and this is allowing us to breathe, in fact. But I cannot enter in this, but it's very interesting. So, first step, energy, work, and then we are coming back to the idea that the energy, the force can be translated as a pressure. Okay? So, the work can be written like minus P dV, then the ambient pressure that is acting toward the system, plus the surface tension multiplied by dA. We already seen that the first day, okay? So, in fact, what is possible to say is that the pressure in the drop is higher than the pressure in the air. The pressure in the drop is higher than the pressure of the ambient, let's say, because there is the surface tension that is keeping the droplet together, okay? This is keeping the droplet together. So at the end, what we have is that we can write the work in this way. So with the expression that you can see here, and of course the volume is going to be the volume sphere, and then sigma multiplied by the differential of the surface, and then we are landing in this case, and when we have the equilibrium, when we don't have any extra force, so when the W is equal to 0. And so you can write down this equation, and it's very simple to see that it's 2 sigma divided by r. Okay? So this is an expression giving now the pressure that we have inside the droplet. So the excess pressure in the droplet with respect to the ambient. Maybe one of you already know that, so it's not a problem. I think that is somehow easy. When we have another force, for example, gravitation, gravity, what is happening is that we can compare this kind of pressure with the hydrostatic pressure. So we can write the expression in this way. So instead of r, I put the diameter. So instead of, let's say, 2 sigma divided by r, we have 4 sigma divided by d. So we have from one side the buoyancy and the other side the capillary pressure. Okay? And we can compare. And if we are comparing, we are getting this diameter that is a kind of critical diameter that is equal to 2 multiplied by sigma divided by delta rho g, okay? This can be written even in a number called bond number, which is a rho delta rho g divided by sigma. But what is this critical diameter? Well, if we have a system that is above this dimension, means that the gravity is acting on the system and the droplet is really, the droplet or something else, but is really very unstable. So it's very difficult to have, for example, one droplet that is bigger than the critical diameter. For example, you're not going to have droplet of rain droplet of bigger than 6-7 millimeters. It's really difficult. It's already 6-7 millimeters is a big bullet, right? So what is happening in space? Well, in space we can have droplet like 10 centimeter of droplet. We can have really big droplets because, of course, there is no buoyancy, because the buoyancy is pretty small in terms of small jitters that we may have on the International Space Station and so on. So, I need to accelerate a little bit. Yes. So what is possible to see here is that I don't know. No. Okay, there is because here I don't see this line. This line here is not present in my monitor. I said, oh, again, something wrong. No. It's a question of resolution here, so it's okay. If you don't consider a sphere and you have a curved surface, whatever, ellipsoidal, everything, what do you think? Okay, it's possible. I'm not entering the details of the demonstration. It's possible to write that instead of having, let's say, 2 sigma divided by r, we have in fact the radius of curvature in the two normal directions. So, in fact, the more general way to see the Young-Laplace law is to consider that the pressure delta P is equal to sigma multiplied by the sum of the curvatures that we have on the surface. This is valid for any surface and not only for a sphere. Of course, for a sphere, it's going to be 2 sigma divided by r. There is also a very interesting thermodynamic approach because usually, when you have a composite system, we have a phase 1 and phase 2. We did this, right? Now, let's consider the interface another thermodynamic system. Okay? So, in this case, we have 3 systems. We have the phase 1, the interface, and the phase 2. Okay? So, we can write the fundamental equation for the Helmholtz free energy, F equal to U minus Ts, okay? And we consider the interface, finally, okay? So, we consider the fact that dF can be written like minus S dt plus sigma dA and int, so the interface. So, this is going to be the force, and we can consider the interface as a system, but with negligible volume and mass. Okay? So it exists, but with negligible volume and mass. And one can say then, when the mass is 0, of course the system doesn't exist in thermodynamics. Okay? But this is now, we are thinking that it's not 0. Okay? It's negligible, it's small. So in this sense, we could put away this term that is related to the number of moles in the interface in the system, and we are landing with this expression, which is a very interesting expression because it contains the entropy, the variation of temperature, sigma, and the variation of the area. Okay? These are not negligible. The other one can be neglect. Okay, it's not 0, but we can neglect with respect to the other 2 terms. So, when we have the equilibrium, when the dF is equal to 0, so we can sum the differential of the Helmholtz free energy for the phase 1, for the interface, and for the phase 2, and we can write down this expression, since a very long expression, but then we can use the equilibrium conditions. Okay? And the equilibrium conditions are these ones. Of course, as we have already seen, the total volume should be conserved, the total number of moles will be conserved, the temperature is the same at the interface, and also and the surface and the temperature should be the same at the interface. So we can write then again the expression, and we are landing with these terms, only with these terms. We can do some algebra. And then, since this equality is must be valid for any dn1 and dn2, or dv1 and dv1, so what is possible to write is that these two chemical potential are the same. This is in fact true because we saw from the phase change, my third lesson, that it should be like that. So at the end, we have the difference of pressure is equal to the sigma. This is thermodynamics now. There was no force. It was really, I've written that in terms of Helmholtz free energy. We are going to have the dA int, so the variation of the area with respect to the volume is giving the pressure, the delta P. So in fact, this is very interesting because this is a so-called generalized Laplace-Young equation. And dA of the interface divided by dV is going to be the mean curvature K. This is particularly important at the nanoscale. Okay, this is particularly important, the nanoscale, how to treat the change of the interface when you are dealing with the surface tension. So let's enter now in the dynamics. So we would like to understand how to deal with let's say the motion of bulk with an interface. So you have a flow, but there is a free interface. So of course, with respect to the equation that I show you in the second day, okay, about Navier-Stokes equation and so on, we need to add now the effect of the surface tension. Okay. First of all, a couple of things. Reynolds number, we know this. Weber number is very important. Weber number can be defined as the ratio between the kinetic energy, rho u square L, divided by the kinetic, by the surface energy. The Weber number is very important in this field. We have also other two numbers that are very important, is the density ratio between the liquid and the gas, the viscosity ratio between the liquid and the gas, and the bond number, that was the number that is coming from the critical diameter. So it's deciding the ratio between the buoyancy and the surface tension. Pay attention that G here is any kind of acceleration of the bulk. So, for example, if you have a centrifugal force, this will be the A there. Okay, the G is becoming A. And of course, you can recognize already that in microgravity in space, the bond number is equal to 0, or very close to 0, because the G is only linked to the jitters and nothing else. And then we have the Ohnesorge number. The Ohnesorge number is putting, let's say, inside this kind of equation, the role of the viscosity. Okay, the role of the viscosity. These are the Navier-Stokes equation with the interface boundary conditions. So this is the equation for incompressible Newtonian fluids. Again, we have that the divergence of the U is equal to 0, so we are considering incompressible flows. The equation is the equation that you saw during the second day. I already spoke about that. Where is the surface tension? Well, the surface tension in the first approach can be, is at the interface. Because you remember that I did all the demonstration of the conservation of momentum looking at the cube. It was a volume of, and then I considered various phases, and we did differences. Okay, and one term of the stress tensor, the molecular stress, was the pressure. Okay. Now what is changing? It's changing that the surface tension is giving another pressure. We saw that. Okay. So in fact, the surface tension is entering inside because at the interface, we can write that we don't have only delta P, but we have delta P plus rho multiplied by K, where K is the curvature, is 1 over R. So the stress balance is changing at the interface. we don't have anymore only the pressure, but we need to add the effect of the interface. Then also we need to consider that we have on one side liquid and the other side gas, so we may consider the so-called kinematic condition, so that the velocity is not going to change. So this means that if we are going to move the liquid at a given velocity, also the gas should respond with the same velocity. Okay? So it's a kind of no-slip condition for the interface. So like when we have a wall that is moving at a given velocity, also the fluids will have the same velocity. No? We are doing the same for the liquid and gas.
What if there is a relative velocity between the phases?
This is at a macroscopic level, it can be. And in fact, in order to simulate what is happening, we are introducing a slip velocity. So you need to, like also for the wall, in some cases, for example, there are some, in order to avoid the so-called kinematic discontinuity when you are dealing with contact angles, this is something that I cannot treat now, but then you need to have, one solution is to have a slip condition at the wall, okay? The same thing is there. So you need to allow that, for example, when you are doing a Euler-Euler simulation, and you want to have the two velocities are different at the interface, you need to introduce a slip velocity. Otherwise, you should have the same. In fact, VOF is, when you're looking at the interface and you're doing VOF or level set and so on, I said very particular cases, someone that tried and so on, the velocity is the same. So you need to have the continuity, the kinematic continuity.
But will it not be clashing with this kinematic condition is actually an interfacial jump condition?
Yeah.
So will not be clashing with the slip velocity concept?
The scales are different. The scales are different. So if you're doing a VOF simulation, so this must be, is correct, no? Because you're considering interface. When you're seeing at the macro scale, so you're doing, for example, Eulerian, we know that from the experiments that we saw a different velocity. But in fact, we saw the different velocity because we are not able to go to the nanoscale. So the scales are different. If you're going to the nanoscale, if you're doing molecular dynamics, you will see that there is a transition not only of the density, but there is a transition of velocity. When there is a, let's say, a K that is going to 0, you're thinking to that, right? When you have a liquid film that is flat, okay? I think so, yes, like that. We are thinking to that. So you're thinking to an interface that is completely planar. Well, we don't have an effect. Very simple. There is no effect. When K is equal to 0, sigma, this term, doesn't exist anymore. Only, but what is happening? You will see now that, in fact, all the theories, for example, the mathematical theories related to, for example, a liquid jet breakup, are considering fluctuations, are considering instability. It's the instability that is going to produce finally the droplet. So every time that you have a flat liquid surface, you don't have an effect. Only, in fact, imagine to have a liquid surface like that, and then what is happening, where is the most important point? It's not here, but at the wall. At the wall is going to be important because we are going to have a change of the curvature at the wall with the effect of the contact angle and so on. But here in the middle, there is no effect of the sigma. Only when you are perturbing it. If you are perturbing the surface, you are giving locally a difference of curvature, then the surface tension is playing a role. But if it's ideally flat, there is no. When you have, but usually when you're doing simulations like that, over, for example, liquid film on a tube, sometimes are the numerical instabilities. The numerical instabilities are enough to produce something. But if you have an ideal case, and so you have a flat surface, there is no effect of surface tension anymore. It's something there is, but it's far. It's not local. K is equal to 0. We need to live with this. Another point is the heat transfer with interfaces. I'm coming back to this point, though. In the next lessons, I'm going to speak about CFD modeling with surface tension, and I will speak about that. But it's very clear from the equations. Then, heat transfer with interfaces. An interface is osmotic, so allows let's say the species, no, from one phase to another, okay, and of course it's diabatic, so it allows the transfer of energy, okay, and this is very important because through the interface we may have, let's say, the phenomena like evaporation, condensation, boiling, phase changes, and so on. So the interface is very important. Another very interesting sentence is always saying that the interface are the devil of the fluid mechanics, no? Because it's really something difficult to interpret because it's a very multi-scale phenomenon. So again, as I said, it's going from nanometers to microscopic effect. And we are not able to solve at the moment. We don't have a simulation that is going from nanometer to even millimeter now. So the hydrodynamic, stochastic hydrodynamic simulations, I'm doing these simulations in a domain of 500 nanometers. And it's already very long. So because it's statistical physics, but I mean, the domain is really very small. So now what there is, I spoke at the heat transfer, I had the plenary lecture at the Olympic of heat transfer very interesting because I said, okay guys, what is now really the big topic in this kind of research is how to match what we have in nanoscale and mesoscale toward what we have at the microscale. We are not able. Someone is working with molecular dynamics. My colleague for example, in Nottingham, they are working with, and in London, they are working with, let's say, molecular dynamics and are trying to match the molecular dynamics with the continuum mechanics. So this means VOF simulations. Okay, this is an approach, of course. Someone is doing with Boltzmann. With lattice Boltzmann solutions. So again, to try to mesh the two things, again, very complex because then you need to consider different phenomena at the mesoscale. The approach of the stochastic hydrodynamics, I'm not the inventor of this, but for example, there is a very important person colleague in Italy, Carlo Massimo Casciola. They are doing an approach where they are treating the continuum mechanics from the mesoscale, so few nanometers up to, in theory, then they can go really far. The problem is the computational power. The problem is the computational power. So you need to stay with a very small cube because then it's becoming really too long. But in principle, they could continue because the equation is the same. But it's complex. So, to come back, what is interesting for us is to understand, for example, the evaporation. Okay, so we would like to understand a little bit more what is happening when we have an isolated drop. So it's not a sessile drop. So the droplet is not on the surface, and we would like to understand something more about the evaporation. And again, we are considering a sphere, This is again very bad, I know, because the droplet can be deformed and so on, okay? But let's say it's interesting because we can, at least mathematically, we can treat this situation. Other colleagues in Bergamo, for example, in Italy, they are, let's say, working with ellipsoidal droplet, not spherical, ellipsoidal droplet, to understand the situation, and so on. What is also interesting is that when we have a droplet in this condition, that is falling, for example, in a gas, we are producing vortices, wakes, and we are going to have also internally a circulation of the liquid, which makes the things a little bit complex because we have an external and internal convection, because the liquid is moving inside and outside. Okay, so. And this means that when you're dealing with the droplet that is falling, the presence of the buoyancy is changing the symmetry of the problem. And in order, if you want really to consider what we are doing in mathematically, you need to go in space. This is, for example, a combustion in space, and you can see that, of course, without gravity, the combustion is happening in a sphere, and not like for a candle that is going. We have a buoyancy. So, and it's very interesting because, of course, if you burn a droplet, no, and you are burning in a spherical form. You don't have the capacity to bring the oxygen inside. It's only by diffusion, because then in the case of the gravity, the fact that we have buoyancy is helping then the gas, the air, to enter inside. They continue to the combustion. So the effect is quite interesting. Is another chapter. Okay. There are many possible dimensionless numbers to consider here. And this is only a table to represent all these numbers. So, since I have, let's say, only 20 minutes, let me speak about a couple of models, only a couple of models. Then there is a couple of books on the topic, so that I will give you at the end. So, one way is the so-called infinite thermal conductivity model, which is consider this model is very basic, but because it's considering that the K, the thermal conductivity of the liquid is infinite. Okay, so but let's say the energy balance equation is a wall. No, it's different. No, this one is different. Sorry, but it's using many CFD. Simulations. The droplet are assumed as an opaque gray sphere, and the droplet radius is assumed to be constant during each time step, and kinetic molecular dynamics effects are completely ignored. So, if we have, for example, radiative heating of droplets, and the droplets are considered opaque, of course, the flux, the heat flux, can be written in this very, let's say, simple equation, where we can have also all the terms. Sigma now is not a surface tension, sorry, but it's Stefan Boltzmann constant. So we have the heating by convection. This is again quite simple, because we can think that the variation of the internal energy inside the droplet, the U, is equal to, no, in this case U, not the U, delta U, is equal to the heat transfer by convection. So it's the surface A multiplied by H, the convection coefficient, multiplied by the difference of temperature between the gas and the temperature. Why we are saying that is infinite the conductivity? Because we are believing that the temperature of the droplet is the same, is constant inside. So there is no difference in this case of temperature between the internal, an internal point in the liquid and the interface. So we are saying the droplet is at the temperature Td, without considering the fact that there may be, there will be for sure, a difference of temperature also inside. Okay, so especially, I mean, not if it's completely symmetric, but it's falling, for example, falling droplet and so on. So you have a breaking of the symmetry, so then you have a change of temperature. So the solution is pretty simple. This is an exercise that I'm giving to the undergraduate students, so I don't want to enter in this solution. The things are becoming a little bit more complicated when instead of an infinite conductivity, we have an effective conductivity. So if you're considering the radial direction, the question is becoming complex, a little bit more complex, because we have, of course, to consider the radial direction in a sphere. Okay, P1R can be in this case, is a term that is linked to the generation of power due to the external radiation. In this case, we are considering, let's say, that there is a radiation that is going to the droplet and is absorbed by the droplet. So we consider like an internal generation of heat due to the radiation that is arriving to the droplet. Then in this case, we can write the boundary and the initial conditions, and we can say that the heat transfer coefficient, Tg minus Ts, this is the convection, let's say, will be equal to to plus KL, the T over the air. This is the classical conduction. But also we have another term that is linked to the fact that we have a variation of the radius in time. Okay? So if you are writing like that, considering an effective conductivity, and the effective conductivity is written in this way, where the Peclet number is the Reynolds multiplied by Prandtl. So we have an expression. We are landing already with something like that. We didn't do so much, right? But the expression is possible to write mathematical these things, but it's becoming already quite complex. I didn't do anything else. I consider that, okay, instead of a k that is infinite, we have the k that is a value. Not even the right k, is an equivalent k. So an effective k, an effective thermoconductivity. We have this expression, and we like to solve mathematically. Well, it's becoming interesting. Because the expression is already quite complex. So only to say that mathematically can be very challenging. Very challenging. Now, there is also another chance that we can consider, let's say, the expression, considering the fact that we have, we would like to understand what is happening in terms of profile of temperature, what is outside and what is inside the droplet. So we are considering also the air, because close to the droplet, the temperature of the air can change. So I would like to understand what is happening inside and outside. This is, for example, very important for evaporating droplet. So I'm going to write the expression considering this equation for the gas and for the liquid, and we need to put together the two equations. The things are becoming even more complicated. Okay? But this is something that was done in the past. I mean, this kind of work is in 1977, so from Cooper. Okay, so if you are going to this paper, so you can write you can see the demonstration, and these are, let me say that are the old times where we didn't have a computer, so all the calculations should have been carried out with using mathematical formula and so on. So, and this is the solution for this case. Okay. Is again, this is a solution. In fact, it's becoming a kind of complex exercise of solution of PDEs, a mathematical solution of PDEs, so partial differential equation, with the different conditions and so on. There are really books on this kind of solutions. What is important for us is that the Nusselt number can be written, let's say, in this form. And when we are considering, for example, a spherical droplet in a quiescent air, Nusselt number is something like the Nusselt number for the sphere. So it's equal to 2. Okay? When we have the motion, so we have a Reynolds number, we are landing with this kind of expression. So, and there are, let's say, other expressions. It's not the only one, of course, because it's a semi-empirical correlation. So there are other expressions, like the other one and so on. But what is important, as we know, because I presented this when I did the heat transfer, no? Nusselt number is a function of Reynolds and Prandtl. So we can use Reynolds and Prandtl to, for this kind of problem. So to evaluate how much is the H between the droplet and the gas phase. So, until now, what we are missing? We are missing now the fact that, this is a problem of conduction. No? I use the heat equation as a problem of conduction with the convection as a boundary condition. So, it's a conduction problem. The convection is entering inside the equations because it's a boundary condition inside the solutions. Okay. But we know that a droplet inside gas may evaporate, for example. Okay? Or we have condensation, it depends on the temperature. But let's say there is a phase change. Now we need to consider, let's say, the phase change. But in fact, what we are considering is the evaporation. So we need to consider not only the heat transfer, but the mass transfer. Okay? This is another chapter. Again, I could speak about that. So another hour only on the basics of the mass transfer. Allow me to be very fast in this case because there is no time. But what is important is that the mass transfer originates by the fact that we have different concentration of moles. Okay? So what is happening is that we have a given concentration of moles of liquid, water, okay? And outside we don't have water, but the interface is an osmotic wall. We said that. This means that it's allowing one species to move to another if we have a difference of chemical potential. And this is just what is happening. So we have a difference of chemical potential between the droplet, the liquid bulk, and the water, the component of the inside the droplet, outside. So this means that molecules are moving of the liquid, of water, are moving from the droplet to the environment. Vice versa, we can have we have gas that is moving toward the bulk of the droplet. Okay, so in fact we have an exchange of components, chemical species, or let's say maybe the same one because we have the droplet inside its own vapor. So we are not changing the chemical species, but we are changing the phases. And we have diffusion. This is let's say, the molecular diffusion. So this means that, in fact, mass transfer by diffusion is very analogous to the heat transfer by conduction. Okay? So this is the point. The equations are pretty similar and so on, but we need to add them and to understand what is happening. So when we want to, for example, to deal with the droplet evaporation, the goals of our, let's say, our work here is that we would like to know the time of evaporation as a function of the properties of the liquid, the vapor, and the environment, the heat flux due to the vaporization, and the temperature time variation of the drop surface. Consider that this kind of goal is very similar also for the liquid film. So we have a liquid film that is evaporating, and we would like to know which is the variation of the thickness of the liquid film due to the evaporation. Okay? This is an exercise I'm giving to in my course. So please calculate with the variation of the liquid film thickness when you are considering the mass diffusion from the liquid to the environment. Okay? So if you are assuming, for example, that the symmetry is spherical, so we don't have motion, non-radial motions, we have a steady state in the gas, that I don't have the word. I mean, the mass flow rate linked to the vapor is constant and depend on radius. The large distance between the droplets, so there is no interaction between droplets, and we don't have chemical reaction. Okay, so if you consider these kind of quantities, the droplet diameter at a time, that is really the goal. The initial droplet diameter before evaporation begins. The mass transfer coefficient, okay, mass transfer coefficient for vapor in air that is linked to the mass diffusion. The density of the liquid phase, the droplet material, the initial mass fraction of vapor in the surrounding air. So it's also important to know how much is already the concentration of the component, the liquid in this case, in the gas phase. Okay, and the mass fraction of the vapor in the surrounding air far from the droplet, at the infinite. So if you do the theory, and I have in the supplementary material, you are landing to this expression. This expression is interesting because it's saying that the time to, let's say, to extinguish the droplet, so that we have at the end no droplets anymore. So it's a the complete evaporation. Let's say like that. The complete evaporation is in fact proportional to the initial dimension of the droplet squared. Okay, so this is a very well known in the droplet evaporation, is the so-called d-square law. So if you are doing a graph with considering all the other factors, for example omega, no, and the mass diffusion coefficient, you can draft very easily this what is happening considering the time and the initial dimension of the droplet squared. Is going to be linear with the surface, because the square you can write in terms of the surface of the droplet, right? Okay, so there is a pi, but at the end the difference is pi, but is in fact the surface. So the evaporation time of the droplet is proportional to the initial surface of the droplet. I added, there are assumptions, but no. Let me say something, sorry. This is important. Because the assumptions are very important, because then when we are dealing with the CFD modeling, we need to consider this. Okay. Which are the assumptions behind this expression? Again, without demonstration, the demonstration I put the demonstration in the last 3 slides of this lecture, but I'm not going to do it because we don't have time. But you can find also in many books, so it's very easy to find. So one assumption is that we have a spherical symmetry, so one dimension, and the convection is not considered. So this is really very important, because if we have convection, natural convection, forced convection, this time is changing. The droplet is isolated, immersed in an infinite environment. The liquid doesn't move relative to the droplet center. Okay, so we have really a kind of movement in this way, but there is nothing internal, so we don't have any deviation, let's say. The process is isobaric, constant pressure. Okay, the gas transport properties are the same, so gamma is the same value. All over, okay. Then the other hypothesis, the gas phase quasi-steadiness. So this means that what is happening let's say is in the liquid in terms of temperature, species concentration, and so on, is pretty much slower, than what is going to be the diffusion. So if you have a change inside, this is very slow with respect to this amount of molecules that are leaving the droplets, the time for this process. We are not considering the opposite directions. We are not considering the gas that is entering in the droplet now, okay? Only we have the liquid that is evaporating into the gas. And again, this is constant and uniform droplet temperature. So this is an infinite condition of the temperature. And then we have at the droplet surface the saturation vapor pressure. Yeah? So this is again the process that I said is very slow with respect to what is happening outside. So there is no mass flow because of the temperature gradient, because the temperature is a gradient. So this means that we have a mass flow, and also the heat mass could change. So we have no Soré or Dufour effects, and we have no radiation effects. So it's quite simplified, but it's interesting. And if you want to know much more about this kind of processes and the mathematical derivation of the equations, you can read one of the two books. This is the first one. This is the second one. And this is mainly they are treating the problem of the evaporation and condensation in droplet, in single droplets, or in sprays. Okay, it's not about the physics of phrase everything. It's about really this problem of evaporation condensation. In the supplementary material, I solved one problem. Let's say about the time of evaporation. Okay, the evaporation time, and this is the demonstration of what is happening. How is possible to derive the equation with the dependency of the evaporation time with the surface of the initial droplet, the initial surface of the droplet. Is a challenge for me to arrive o'clock. Okay, I did it again. So good. Yeah, we have I think a break, right? 5 minutes, 10 minutes break.